So let's do an example. So for example, I have a random variable which now takes integer values. It doesn't have to, but this one does. And suppose this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So this is my random variable. It takes value from 0 to 15. And this is my probability. So this is, this is unnormalized probability. You can normalize it. So this is, so the probability of getting 1 is 1. The probability of getting 2 is 2. The probability of getting 3 is 1. 4 is 3. Okay. 5 is 5. Sorry. App is doing something on its own. It's alive. Okay. Sorry. 4 was 3 and 5 is 5. And say 6 is and 3. And then 7 is 2. 8 is the same as 4. 9 is 2. And no, 9 is not 2. I think 9 is going to be 4. 10 is 2. 11 is 2. 12 is 4. 12 is 4. 13 is 2. 14 is 1. 15 is 1. So this is, this is x, and this is p of x. Okay, so this is basically what a probability distribution looks like. So you can see that this is something that you can think of it as a discrete function. Okay, and the average is, in some sense, you're finding its center of mass. Okay, so now if you calculate the average, it's a very easy calculation. You can find that the average is 7.825. So the center of mass is somewhere like between 7 and 8. So it's somewhere here. Okay. This is where the average is. But as you can see, the average is not going to be the only data characterizing. It doesn't tell you what the distribution looks like, right? So you need higher order moments to give you what the distribution looks like. And the most frequently used higher order moment is the variance. But before we go to that, let's, here we just are calculating the function, the random variable x, but you can also calculate, the function of the random variable x, say f of x when f of x is x squared. So if you do that, then x squared, you can verify is 73.625. Okay. So now we are going to talk about variance, but before we do that, do you follow why I want to talk about variance, and any other question?
I have a question.
Yeah.
I have found that there's some ambiguity, at least to me, what the difference between a distribution and a function is. Like there will be probability distributions, and it's incorrect to call them functions, maybe. Like generalized functions is what they're called.
Right. So probability distributions are not really functions, because functions, well, it depends on what you mean by function. Usually, in real analysis, it's very contextual. If you're in real analysis, then your function has some very nice continuity properties, whereas here we see that we are dealing with a quote-unquote function that is a discrete thing. So the idea of continuity is not here, right? So, you can think, So it's really contextual. You can call this a function if you like. I have no problem, as long as you mean that, oh, this is a function of a discrete variable. We are calling it a probability distribution because of the context. The context here is that this is a function of a variable which is a random variable. Means that it takes values from a certain set, and the probability of the value that it takes is given by that function. So it's about context. Now, the idea of generalized function is something different. The generalized function is something which is in the realm of real analysis, but it doesn't have the nice differentiability properties of a function, but still is quite useful. For example, the Dirac delta function is such a function. It is not a continuous function, but it is still is a very useful function. And then, for example, the Heaviside step function is another example of a generalized function. So a generalized function is slightly different. It's basically a function which is you're talking in the realm of real analysis, but it doesn't. But they are somehow, you have to loosen some of the restrictions that you put on nice functions there. Okay.
I see. Thank you.
Okay. All right. So so the idea of the variance is that it's telling you how spread out this value is. So for example, you know that the average is here, but if you are going to, you know that the probability of being here or here is actually quite high as well. The probability of here is very low, but here is low, but over here and here in this region is high. You want to find out what that is. So that is known as the variance, or you can think of it as the second moment, the first moment, no, the second moment, I guess. So it's defined as delta of f to be the difference, that the value that the function takes from its average, the deviation from its average. But then what you want to do is that you want to take this average. But if you take the average, then this is going to be 0. Because there'll be positive terms and there'll be negative terms. So what you want to do is that you then square it so that everything becomes positive, and take the average of that guy. But then you have taken the average of a square, so you want to do a square root. So this is known as the root mean squared, or the variance, or the standard deviation, okay? And what the variance does is that it tells you like how spread out your values are. And you can even have higher order functions. So, I mean, the variance, of course, tells you how spread out this is, but of course, it doesn't tell you everything about this distribution. And there are higher order quantities that you can consider, such as, say, skewness. For example, what if there was a lot of values here? Then the distribution would be skewed. So the third moment is called skewness, and then there's a fourth moment, it's called kurtosis, and I don't think there's a good name for that after that. So this is the discrete analog of what we are doing here. This is the discrete analog of Taylor series of a function. Okay, just going back to the idea, the discussion, the question that we just had about functions. Anyway, we are not going to be worried about these higher analogs, higher moments now. So here, what we want is that, it's easy to see that if you expand this square now, then you're just going to get the average of the square of the average minus the average squared, and then the whole thing square root, okay? The cross term cancels out. The cross terms cancel out, okay? So this is a very, and often it's easier to deal with the square because then you don't have to deal with the square root, okay? So this is a very nice expression for the variance squared. And now if I go back and say, what is my delta of x is, then my delta of x for the set of data that I gave, it's going to be 73.625 minus 7.825 squared, and then the whole thing square root, and I take it to, 3 significant digits after then I have 3,521. Okay, so what it's saying is that around the average, which is over here, we can go 1 to 3.5. This is the region that the value is that we can find the random variable to take, to be found most probably. Okay.